Okay, let's on.
Hi, everyone. Welcome back to another meeting of Alcoholics Anonymous. This is where you feel safe. You can free to talk about anything you want, or maybe not. Today, we'll have a speaker, Noé Durancourt from Kurt Gödel Research Institute, and he will speak on local Banach space dichotomies. Noé, take it away, please.
Thank you. So thank you. My name is Noé. I'm an alcoholic. Sorry, I do Banach space theory for 6 years now. Okay. So yeah, first, thank you, Benjamin, and thank you for organizing this seminar. It's very nice. And yeah, that's a good thing to be able to meet with everybody in the whole world every week. I mean, even without the corona situation, I'm in a place currently where there is where there are not so much Banach space theorists. So that's a good thing for me. Thank you. And so today I will be talking about a common work with Wilson Cuéllar-Carrera and Valentin Ferenczi, and it's about local Banach space dichotomies. So what are local Banach space dichotomies? It's basically dichotomies of Banach spaces where the space given by the dichotomy, the outcome space, can always be taken in some family of Banach spaces that is prescribed in advance. So for example, one of the main examples of such a family is the family of all non-Hilbertian spaces. So this work comes from a paper that has been put on the archive something like 1 month ago. And the title of the paper is Local Banach Space Dichotomies and Ergodic Spaces. So you can see that here in the title of the talk, I removed one part of the title of the paper. It's just because the paper is quite long. It contains quite much material. So I will not be able to talk about everything. I choose to give more details about some aspects and less details about some other aspects. So in particular, so some of the material presented in this paper is quite old. We started to work about this several years ago, and I've already presented some preliminary results at some conference that maybe you have seen. So, for example, if you were in Ubatuba 2 years ago or in Métabier 1 year ago, you may have heard me talk about that. And at this time, I was mostly talking about the results we had at this moment. That is the special case of the family of localizing dichotomies to the family of non-Hilbertian spaces and the application to ergodic spaces. So today I will be talking about mainly the dichotomy part of the thing, of our work, and I will be more concentrating about how to generalize this to a large spectrum of families of Banach spaces. So first, before everything, just recall the terminology I will use during this talk. So of course, as usual, all my Banach spaces will be infinite dimensional unless otherwise specified. Sometimes in the talk I will use exceptionally finite dimensional spaces, but at this moment I will precise it. And by a subspace, as usual, I will mean an infinite dimensional and closed subspace. I will say that a space is Hilbertian if it is isomorphic to a Hilbert space, not necessarily isometric. And of course, and so I will work in real spaces, but everything I will present will work as well in complex spaces. So first, to motivate everything, what I will talk about today, I will recall some basic facts about Gowers classification program, which is the reason why we need or we want to prove dichotomies. So it's in some ways a motivation of this talk, even if our initial motivation was different. This can be seen as motivation of this talk. So as all of you know, I think, as anyone who has experience with dealing with Banach spaces, you know that there is no hope classifying separable Banach spaces up to isomorphism. The diversity of separable Banach spaces is too wide to be able to hope for such a classification. And this statement was even in some way formalized by Ferenczi, Louvot, and Rosendahl in 2009. They proved in a descriptive set theoretic formalism that in some way this classification problem, the classification problem of Banach spaces, of separable Banach spaces up to isomorphism, has the highest possible complexity among all classification problems of countable or separable structures. So I won't give more detail about this, but that's something you can do. Of course, that's something that was intuitively known much before that. And for this reason, Gowers suggested in his famous paper, An Infinite Ramsey Theorem and Some Banach Space Dichotomies, which was published in the Annals, he suggested a weak classification program for separable Banach spaces. And his idea is to classify Banach spaces up to subspaces. So what do I mean when I say classifying up to subspaces? I'm just saying that the goal is to build a list of classes of separable Banach spaces. So such a list is usually called a Gowers list. So a list that is as fine as possible. I mean, I want it to contain as much class as possible, and I want the class to be the most precise possible. So a list of classes of separable Banach spaces satisfying the following conditions. So first, I want the classes to be hereditary. By that I mean that I want that if X belongs to a class C, then all subspaces of X also belong to C. Or sometimes, usually in such a classification, some classes are defined using properties of bases of the spaces they contain. So in this case, you will define hereditariety as being stable under taking block subspaces, for example. So for example, if your class C is the class of all spaces having an unconditional basis, then of course your class will be closed under taking block subspaces relative to this unconditional basis. So second condition, the most obvious one, the classes are pairwise disjoint. And Gowers in his paper even precises, I want the classes to be very obviously disjoint. In most cases, the classes will not only be disjoint, but even disjoint in, I mean, radically opposite one to the other. Third condition, knowing that a space belongs to a given class gives much information about the structure of this space. So that's an important condition because it's what prevents your classification, your classes to be made ad hoc in some way. So for example, you could imagine a classification like this with two classes, the first class is being the class of all LP and C0 spaces, LP spaces and C0, and the other class being the class of all spaces not containing any copy of LP and of C0. But in this case, this second class won't be interesting. You won't have nice property on it because it will be defined by a negative property in some sense. And to finish, the last property that you want that every Banach space contains a subspace belonging to one of the classes. So you don't classify all separable Banach spaces. You only classify in some sense small Banach spaces. So for example, if you are given such a list, of course C01 will never be in one of the classes because by hereditariety it would mean that everybody in this class is in this class. But what you want is that every space contains a subspace belonging to one of the classes, and it's the reason why it's called a classification up to subspaces. So when you deal with such a classification, when you want to build a Gowers list, usually the most difficult step is to prove property for this property. This property requires to prove so-called Banach space dichotomies. So I'm gonna give you an example which was proved by Gowers, which is now known as Gowers' first dichotomy. That was the starting point of this classification project. So Gowers proved that every Banach space X contains a subspace Y such that either Y has an unconditional basis or Y is hereditarily indecomposable. I recall that a space is hereditarily indecomposable, or HI, if it contains no topological direct sum of two subspaces, so of course of two infinite dimensional subspaces. So of course, this dichotomy provides you a Gowers list with two classes. The class of spaces having an unconditional basis, and then the class of HI spaces. So of course, these classes are hereditary. They are very obviously disjoint and even radically opposite in the sense that if a space has an unconditional basis, then it will have not only one, but plenty of decomposition as direct sums. So the third property is the fact that classes give good property to the space they contain is mainly due to the fact that so of course you know that for spaces with an unconditional basis, it's good to know that spaces with an unconditional that a space has an unconditional basis, and for HI spaces it's the same. We have strong properties of HI spaces, and in particular about their operators. Such spaces have very few operators. And finally, the fourth property is justified by this dichotomy. So I want to point out the fact at this moment that usually such dichotomies draw a line between a class of classical spaces that are spaces that share many properties with, for example, the LPs or C0, and a class of exotic or pathological spaces. So, for example, here, hereditarily indecomposable Banach spaces. So, after that, Gowers proved the second dichotomy that I won't be talking about here. And then some other dichotomies, three other dichotomies, were proven by Ferenczi and Rosendahl. And I will present you one of them, which is the most important of them, which they called the third dichotomy because it comes after Gowers' second dichotomy. So, of course, the first class, the class of classical spaces, will be the class of minimal spaces, the class of spaces that embed into all of their subspaces. So, for example, this class contains C0 and the LPs. And the second class has been defined by Ferenczi and Rosendahl in the same paper. So, if Xi is a family of vectors in a Banach space, I will denote by bracket Xi the closed subspaces they span. So this definition is quite technical, but it's easy to understand. Given a basis EI, we show the basis of a Banach space, and a Banach space Y, which is completely different and related to I, we say that Y is tight in EI if there exists a sequence of successive intervals of integers. So by this I mean all the elements of I0, I0, all the elements of I1, etc. Such that for every infinite set of integer, the space Y cannot be embedded into the base, into what remains of the basis when you remove infinitely many of the intervals AI. So as soon as you remove the infinitely many of the interval AI, you cannot embed Y anymore. So in some way, this means that every embedding of Y into the space generated by the AIs should take almost all the space. I will say that the basis is tight if every Banach space is tight in this basis, and that the Banach space is tight if it admits a tight basis. So tight spaces are an example of class of pathological spaces, and for example, it contains Tierson space. So of course, minimal Banach spaces cannot be tight, or tight Banach spaces cannot be minimal, because the space itself would be tight in its basis, and it could not be embedded too deep into itself. And as you can imagine, the statement of the dichotomy is the following: every Banach space either has a minimal subspace or has a tight subspace. So this dichotomy, if you combine it with Gauer's first dichotomy, this provides you a Gauer's list with three classes. So first, the class of minimal spaces having an unconditional basis. Second, the class of tight spaces having an unconditional basis. And in this case, the tight basis and the unconditional basis can be taken to be the same. And third, the class of tight HI spaces. So you can remark here that there should be a fourth class, the class of HI minimal spaces, but actually this class is empty. It is well known that an HI space cannot be minimal, and of course this class disappears. And then, so as I told you, other dichotomies were proved by Gauers and Ferenczi and Rosendahl, and you can extend this list to a list with six classes, all of whose are known to be non-empty, and 19 possible subclasses. And so now I will give you an example of why this classification is not perfect. Consider gem space. Gem space, it's maybe, I think, the first example of a pathological Banach space, the first example of a Banach space built as a counterexample. And now it has become classical. It has become a classical Banach space. And this space is L2 saturated, which means that a Gauss list will never give any relevant information about it. It has L2 as a subspace. L2 will always be classified in the most tame class of such a Gauss list. So it's totally useless to understand the property of such a space. But this space, I mean, of course, the same holds for C0, but C0 is a very large space. Here the situation is very different. Gem space is in some way small. It is L2 saturated, so you could expect that such a Gauss list should give information about such a space, but not. And there's come from the idea, and there's why the idea of proving local dichotomies come from. So local dichotomies are dichotomies that are similar to the previous one, but where the outcome space can always be found locally, that is in a fixed family of subspaces. So for example, the family of spaces that are non-Hilbertian. So here the word local was stolen to Ramsey theorists. You may know that such dichotomies are usually proved by Ramsey theoretic methods, in Ramsey theory, they have some part of Ramsey theory called local Ramsey theory, where they do exactly the same. They prove dichotomies. They prove dichotomies where the homogeneous space falls in a particular family of subspaces. So in particular, the word local here is not the same as the word local from local Banach space from local Banach space theory, but in some sense it's still related, because the first example we had of families for which we could localize dichotomies were families defined by local properties of Banach spaces. So in some sense, at the beginning of our work, the word local has this double sense. But now, after that, we managed to prove dichotomies for families that were not defined by local properties. So it's more general than that. So what I will do in this talk, I will present you local versions of Gauer's first dichotomy, and then of Ferenczi and Rosendahl's third dichotomy in the formalism of degrees. So the formalism of degrees is a formalism we made up to be able to define families for which we can prove local dichotomies. So this is not the most general formalism we have for local dichotomies, but it's the most meaningful in a Banach space theoretic sense. We have another formalism, the formalism of so-called D families, which has better closure properties, but which is less meaningful, and I don't want to enter into details of this formalism today. So this formalism is made to generalize local properties to some properties that are in some sense semi-local. So let's consider a property P of Banach spaces. I will say that this is a local property. If this is a property that you can have, that a Banach space can have with a certain constant C, such that a Banach space X has property P with constant C, if and only if all of these finite dimensional subspaces have property P with constant C, and such that property P doesn't change a lot. The constant C of the property P doesn't change a lot if you replace a Banach space with another one which is close to it in the sense of Banach major distance. So here, in this definition, I choose to give a multiplicative dependence of the constant, but it could be not multiplicative. For example, like you could replace this kc by k squared c. It doesn't matter. That's just an example. So, for example, such property include being Hilbertian. You probably know that a space, a Banach space, is C isomorphic to a Hilbert space if and only if all of its finite dimensional subspaces are themselves C isomorphic to a Hilbert spaces. This also concerns so such property can be having type P, having cotype Q, etc. So here, for example, the constant C would be the type P constant. And I will, for now, give you an informal fact that I will precise later. Usual Banach space dichotomies can be localized to space failing property P. This means that if we have a local property P of Banach spaces, and if we have a classical dichotomy, then I can localize this dichotomy. I can find a version of this dichotomy in such a way that the outcome space always fails. So I will give a precise statement of the kind of dichotomies we can get after that, but to state it like this informally, and we can actually generalize this informal fact to certain property that are not local, and such property will be defined will be defined through the notion of degree that I will present now. So I just got a message of my laptop telling me that telling myself that my internet connection is unstable. So it's if at some point you don't hear something I say, please tell me.
You're fine.
I think, well,
yeah, you're fine.
Yeah, it's gone, so I think it's fine. Yeah. So what is a degree? A degree is something meant to generalize this constant C that defines the local property, but we want to generalize it in some way that the constant C not only depends on the finite dimensional subspace, but also on how it is embedded in the whole space. So I will give the definition. So I will consider what we call approximation pairs. So an approximation pairs is a pair made of a Banach space, which can be finite or infinite dimensional, but in general it will be infinite dimensional, and of a finite dimensional subspace of X, which is meant to approximate the whole space. So that's why it's called approximation pairs. I will denote by AP the class of all approximation pairs. And a degree will be a mapping which associates to each approximation pair a real number, a positive real number, such that for every operator S and T, such that this diagram has a sense, the following diagram, such that for every operator S and T, that makes this diagram commute, we have that the degree of G in Y is below norm of S times norm of T times degree of F in X. So here, the fact that this diagram commutes, so yeah, I forgot to say that, oh, what did I do? Okay.
You're using distance for degree. It's a little bit confusing there. That's something different, right? So
What did you say?
you're using the distance notation, a little bit confusing, but it's some, you call it degree.
Yes,
Yeah,
you're
okay.
right. Yeah, it will be a degree, not a distance. Okay. The distance are usually denoted by dBm, like Banach measure distance. Yeah, sorry for that. So yes, if you have such a diagram where here the iotas are the canonical inclusions, if this commutes, then it implies in particular that S is injective. And so in general, in many cases, for example, G will simply be a subspace of F. So here you will say that the degree D is local if D of XF only depends on the subspace F. And in this case, it will be simply denoted by D of F. And if D is a degree, then I will say that the Banach space is D small if the degrees of its finite dimensional subspaces into itself are bounded, and otherwise I will say that it is D large. So now I want to point out the fact that a local degree, a degree that only depends on the finite dimensional part, is exactly the same as a local property. So if you have P a local property, then you can denote by D of F the infimum of constant C, such that F has property P with constant C. And then D will be a local degree. And being D small is exactly the same as having property P. So local properties and local degrees are exactly the same. Now, the whole point of degrees is to generalize this to the case when D of F, such that the constant not only depends on the finite dimensional subspace, but on the way it is embedded in the whole subspace. So for example, with a degree which is non-local, you could have an ambient subspace X and two finite dimensional subspaces F and G that are isomorph, that are isometric, but not ambiently isometric, and that have a different degree. And this condition in the definition of degree, this multiplicative condition is just the translation of this multiplicative condition on constant with whom the property P is satisfied. So I will now give you some examples so that it is more clear. So first example, the most simple, the dimension. The dimension is a degree, and these small spaces are exactly finite dimensional spaces. So this is an important degree because classical dichotomies exactly correspond to dichotomies that are localized to this dimension degree. So this means that in particular, our general dichotomies, our local dichotomies, will give back the original dichotomies when localizing to this particular degree. So another example, when the degree of F is equal to the Banach measure distance between F and the Euclidean space of the same dimension. So here this is local degree, and by the remark I just said before, the fact that a space is Hilbertian if and only if all of its finite dimensional subspaces are Hilbertian with bounded constant, this means that these small spaces are exactly Hilbertian spaces. So this degree will be called the Hilbertian degree, and it will be denoted by D2. So please remember this notation and this name. I will talk about it again at the end of the talk. Then, a related example. Consider P a real number between 1 and 2. Then the type P constant of a finite dimensional space is a degree. So you know that a space has type P, so that the type P constant of an infinite dimensional space is equal to the supremum of the type P constants of all of these finite dimensional subspaces. So in particular, these small spaces are exactly those having type P. And you can do the same for cotype Q. So all of these examples are local degrees. Now we will present you some examples of non-local degrees. So I will take P between 1 and infinity, and I will denote the, and I will denote by D. I will define dxf as the infimum of the m, of the constant m's, for which the canonical inclusion of x, of f into x, m factorizes through some LPn. So that means that there exists an LPn, and that there exist two operators like that, such that the product of the norm of these two operators is less than m. And in this case, you get a non-local degree. And what are the properties of this degree? Well, by a result by Lindenstrauss and Rosenthal, we have that if P is strictly between 1 and infinity, then a space is D small if and only if it is either Hilbertian or a script LP space. And if P equals 1 or P equals infinity, then space is D small if and only if it is a script LP spaces. So you can get script LP spaces or Hilbertian spaces as these small spaces for some degree. Another example of the same kind. Suppose that here, instead of taking an LPn, you ask there to be a space with a one unconditional basis. So let dxf be the infimum of m's for which the canonical inclusion of f into x m factorizes through some space with a one unconditional basis. Then then D is a non-local degree, and by definition, a space is D small if and only if it has Gordon-Lewis local unconditional structure. So that's the definition of Gordon-Lewis local unconditional degree, local unconditional structure. So all of these examples actually are particular cases of more general example, and I don't know actually if there are interesting degrees that do not come from such a situation. It's related to operator ideals. So I recall that a normed operator ideal is given by for all Banach space x and y, a vector subspace u x y of all the space of all operators between x and y, and by a complete norm on u x y, which does not need to be equivalent to the original norm, to the original operator norm. And we ask that whenever you multiply an operator in U by two operators that are not in U, that are arbitrary, then you get an operator which is in U. So U is absorbing, it's like in ring theory, U is absorbing, and we moreover ask that the norm of UTS is less than the norm of T multiplied by the usual operator norm of U and of S. And some technical condition, you want that the identity on the scalar on the space of scalar is in the ideal and has norm 1. So that's a quite classical. Thing in Banach space theory. So, for example, approximable operators, compact operators, etc., form normed ideals. And if you have a normed ideal U, then you can define D of xf as the norm of the canonical inclusion of f into x, and then this gives you a degree. So I don't really know if there are interesting degrees outside of that, but there could be theoretically, because for example, here you have the condition that U is a vector space of L of XY. This is an additive condition on norms. We don't have this additive condition in the definition of degrees. So that could be more general. And to finish, a non-example. So let D of XF be the infimum of all the k's, of all the constant k's, such that F is K complemented in X. Then this is not a degree. And this is somewhat surprising because you probably know these classical results in local Banach space theory. I think it's by Lindenstrauss and Shafiri, that a space is Hilbertian if and only if all of its finite dimensional subspaces are uniformly complemented in itself. So this would mean that if D were a degree, then these small spaces would exactly be Hilbertian spaces. But we know that the class of all Hilbertian spaces comes from a degree, but actually in general, this is not a degree. So now let's review some properties of degrees. So if you take D a degree, then all finite dimensional spaces are D small. Even more, if you're given a fixed n, a fixed dimension, then D of F for F of dimension n is bounded by a universal constant only depending on the degree D. Second, the properties of being D small and D large are invariant under isomorphism. Then a complemented subspace of a D small space is itself D small. This is in general not true when you take arbitrary subspaces. So for example, you could have a subspace of a space having Gordon-Lewis and conditional structure, local and conditional structure that does not have Gordon-Lewis local and conditional structure. But in the spatial case of local degrees, then every subspace of a D small space is itself D small. And to finish, property that is not so meaningful in a Banach theoretical sense, but which is very important because that's what you need to prove our dichotomies. It's that we can diagonalize among D large spaces. So if you have a decreasing sequence of D large spaces, then there is a space X infinity which is almost included in all of the term of the sequence, almost including meaning here that a finite codimensional space of it is included in all of the is included in Xn for every n. So for every n, there exists a finite codimensional subspace of X infinity that is contained in Xn. So as you may know, I told you that these dichotomies are proved by combinatorial methods, Ramsey theoretic methods, and actually this ability to diagonalize is the main thing you need to perform Ramsey theoretic arguments. And so I think that now I can present you the dichotomies. Oh no, I forgot something. Of course, yeah, there is a problem. Most of, oh, what? Okay, yeah. In general, most of our most of the classical dichotomies involve classes defined by property of basis. And in this general case, it's not a good thing. It's not something we can have because in general, given a degree D, it is not clear whether every D large Banach space should contain a D large subspace with a basis. So for example, in the case of the Hilbertian degree, this is open. We don't know if an arbitrary non-Hilbertian Banach space should contain any non-Hilbertian subspace having a basis. This is a question that was asked for the first time by Telsinski in, I think, in 64, so it's long ago. and in our knowledge, it's not answered yet. So we'll need to replace bases by finite dimensional decompositions instead of them. So definition, I will say that a finite dimensional decomposition, Fn of a Banach space S, is said to be d better if and only if the degree of the terms of the FDD into the whole space tend to infinity. So in particular, this implies that your space X is large. And in this way, you can characterize large spaces in some way using FDDs. So if that's what I just said, if a space has a d better FDD, then it is d large. And conversely, we can prove that if X is a large Banach space, then it may or may not have a d better FDD, it may or may not have an FDD, but it always has a subspace spanned by a d better FDD. So it's kinda the d large version of the classical fact that every Banach space contains a subspace with a basis. And more generally, all standard results about basis, so for example, Besaga-Pelczynski, still hold for better FDDs. And that's exactly what we need. That's exactly the second condition we need, apart from the diagonalizations thing, to prove our dichotomy. Oh yes, I forgot to say something. It's called better because in our more general formalism, without degrees, the formalism of D families, then there is also a weaker notion of good FDD that I won't present in this talk. So that's why the better. So now I can present you a local version of Gauer's first dichotomy. So we fix a degree D, and we want to localize Gauer's first dichotomy to the class of D large spaces. That is, we want to find a version of this dichotomy where the outcome is ensured to be D large. So that's a supplementary constraint on the outcome. So this is strengthening, and it comes at the cost. The cost is that the two possible conclusions of the dichotomy have to be weakened in some other way. And in particular, you need to weaken the notion of HI spaces. And I will give you the definition now. I will say that a space is DHI if it is D large, and if it contains no topological direct sum of two D large subspaces. So for example, if you take D to be the dimension, you get exactly the definition of D of HI spaces. D large spaces, when D is the dimension, are HI spaces. But in general, this is weaker because you only ask your condition of no topological direct sum for D large spaces. And the dichotomy will be the following. If we take X a D large Banach space, then it has a D large subspace Y, such that first possibility, either Y is spanned by a D better UFDD. So here you replace the unconditional basis by the UFDD, which is in some sense weaker, or Y is D hereditarily indecomposable. So that's our first dichotomy. And with this dimension, then we recover the original version of Gauer's first dichotomy. So now, a local version of Ferenczi-Rosendal's third dichotomy is the dichotomy between minimal and tight. So in the same way, we have to weaken the notions of being minimal and being tight. For minimality, it's easy. I will say that Banach space is D-minimal if and only if it is D large and it embeds into all of its D large subspaces. So it's weaker than minimality, for which you have to embed into all of your subspaces. And for tightness, it's almost the same definition. So first, you will replace tight bases by tight FDDs. You will say that Banach space Y is tight in an FDD Fi if there exists a sequence of successive intervals of integers, such that as soon as you remove infinitely many of these intervals, you cannot embed Y anymore. So it's the same. Y takes much place in much space into the space spanned by Fi. FDD is D-tight if and only if every D large Banach space is tight in it. You don't ask every Banach space to be tight in it, but only D large Banach spaces. And finally, a Banach space is D-tight if and only if it admits a D better and D-tight FDD. And the dichotomy is what you imagine. Every D large Banach space either contains a D minimal subspace or has a D-tight subspace. So how much time do I have left? 5 minutes, something, I think?
Yeah, about six minutes, yeah.
6 minutes, okay. So that's fine. I was not sure to talk about everything anyways. Yeah, I think that this is the most important thing to talk about. So these properties, minimality, D-minimality, D-tightness, the property of being DHI, that were pre-existing properties, that are properties that actually come from the proof of the dichotomies. And in particular, we don't know much about this property. And there is something very strange about D-minimal spaces that I want to present you to finish this talk. If you take D a local degree, what I will tell you now only works for local degrees, not for non-local degrees. And X a D-minimal Banach space, then there is a mapping gamma from the integer to positive real numbers tending to infinity, such that for every D large subspace Y of X and for every N, the supremum of the degrees of F for F, a subspace of Y of dimension N, is greater than gamma of N. So basically, saying that a subspace Y of X is D large, it's exactly saying that these expressions, this function of F tends to infinity for Y. Yeah, saying that Y is D large is just saying that this tends to infinity when N tends to infinity. But the point is that here, in the case of D-minimal Banach spaces, we have a strengthening of this. For every Y, this has to tend to infinity uniformly. So in some sense, D-large subspaces of a D-minimal space are uniformly D-large. And this is surprising in some sense, because imagine that X is a D-minimal Banach space that is in some way non-trivially D-minimal, that is non-trivial, so that is not minimal. So of course, minimal spaces that are D-large are D-minimal, but there could be other ones. So consider X a D-large space that is D-minimal but not minimal. This is equivalent to say that it is saturated with D-small subspaces. Then this mapping, if the subspace Y is D-small, then it will be bounded. And if the subspace Y is D-large, then it will tend to infinity, but it will tend to infinity at least as fast as the mapping gamma. So there is a gap in the possible growth of the possible growth rate of this function. And from a local point of view, this is something which is somewhat strange and that we don't expect. So for this reason, we are not even sure that for D, a local degree, D minimal spaces that are not minimal exist. So I could ask it as a question: does there exist local degrees such that all D minimal subspaces, such that all D minimal, sorry, it's not subspaces, it's spaces, such that all D minimal spaces are minimal? And does there exist other one for which D minimality does not coincide with minimality? So I would particularly be interested in the special case of the Hilbertian degree. So I will pass this slide. I think it exactly 0 minutes, so I won't spend too much time on the special case of the Hilbertian degree, but I will tell a few words about the consequences. So for example, so our original motivation. So our original motivation was a problem asked by Ferenczi and Rosendahl something like 15 years ago. They are asking whether every Banach space, every separable Banach space that is not Hilbertian necessarily has continuum many pairwise non-isomorphic subspaces up to isomorphism. So if you take a space, if you take a Hilbertian space, of course, it has only one subspace up to isomorphism. If you take a space that's not Hilbertian, you necessarily have continuum many pairwise non-isomorphic subspaces. I wrote here the more general form of their question actually, but I don't want to explain it into details. For those who know what is E0 and what is Borel reduction, they can understand, but for the other one, for the other people, I don't want to enter into details. And with our local dichotomies, we get the following results. We can reduce actually this conjecture to the special case of Banach spaces that are D2 minimal. So that are minimal for the Hilbertian degree, that are exactly those spaces that are not Hilbertian and that embed into all of their non-Hilbertian spaces. So if there exists a counterexample to this conjecture, if there exists a Banach space which is non-Hilbertian, which is separable and which has which has strictly less than continuum many pairwise non-isomorphic subspaces, then there should be such a space which is D2 minimal. And that's an interesting reduction of the general conjecture. And I will stop here. Thank you for your attention.
Okay, thank you so much, Noe. Yes. So can you go back to the very last slide?
Yes, this one.
So does this also, this is something I think we were thinking about it, that actually something you asked on Matt overflow. So the, in particular, you are asking, let's say you have like L2 sum of finite dimensional spaces where it's not, the distance are going infinity. So the question is basically, can you get, are there spaces where we can pass the subspace of the same form which have the same sort of function of distance? So the finite dimensional subspaces have the same function to the distance function, correct? So is that what you're saying? That whether you, I think we don't know if such spaces exist.
So you're asking whether, oh, maybe it's not that slide you're talking about. It was maybe this one, right?
Yeah, so this sounds interesting because you say there is a bound on the function of, but this is for, right. So if it's minimal, then, so you're saying if it's D minimal, then such spaces cannot be in the form that I just said, say L2 sum of finite dimensional spaces where the distance function of finite dimensional subspaces.
Okay, I'm not sure. Yeah, I'm not sure I've understood well your question. So what, can you repeat your question? I think I misunderstood it.
So this question is actually, I think, was your question on meta overflow, which comes down to the question that basically, if you, let's say you have L2 sum of finite dimensional spaces, but the whole space is not isomorphic to L2. So in particular, those finite dimensional subspaces, the distance of L2 is going infinity. And there is some function, right? So dn is some function that's going infinity. So the question is then, what I call actually is that a locally minimal such space. By locally minimal, I mean you can pass to, for every further subspace, the distance function is still same as the original, like dn is same as dny, whether such spaces
so
exist. And,
and
you're saying if it's D minimal, I think what you call D-minimal is exactly those spaces, aren't they? Right.
I think not,
the
because
examples.
what you're talking about would be called, I think, locally D-minimal, probably. But yeah, I think that there do not exist D-minimal spaces for. So, for example, in the case of the Hilbertian degree, I think that L2 sum cannot be D-minimal. But I tried to prove it, but I don't manage to prove it. But I don't think it should be so difficult. I think it's something doable.
Well, if we're talking about the same problem, it's actually, that's what I thought initially too, but it turned out to be much harder than I thought. We thought about it a little bit.
Okay.
So, but I'm not sure if we're talking about the same problem. So anyway, maybe we can talk later.
Yeah, maybe you can talk, but yeah.
Okay. Any others?
May I ask a question? Sorry.
Yes, you can.
So my question concerns in general the classification of closed subspaces of a Banach space. When the classification of definable equivalence relations is used to classify the closed subspaces of a Banach space, and the closed subspace is endowed with a Frost-Borel structure, I was wondering, how do you assure that this structure only depends on the isomorphic structure of the Banach space?
It's a matter of definition. It's a matter of definition, I think, because the definition of the Frost-Borel structure is you're generated by sets of the form, the set of all closed subspace Y that intersect U, for U being an open subspace, an open subset of the whole space, an open subset. So open subsets don't depend on the norm, on the equivalent norms, and they only depend on the topology. So it's a definition that only the topology, but not the norm, but not the equivalent norm, is used in the definition. So that directly gives you that it only depends on the topology, and hence that it's invariant under isomorphism. Was I clear?
Yeah.
Okay.
Yeah.
I have a question.
Yes.
Can you go to the last page, this conjecture of Ferenczi and Rosenthal?
Yes.
So my question is whether it's known under the continuum hypothesis. So if you have a space with only countably many...
No, it's not known.
It's not known?
No, even a very simple case, there is even a very simple case that is not known. It is not known whether there exists a separable Banach space having exactly two subspaces up to isomorphism. Even this is not known. It was a question, I think, asked for the first time by Bill Johnson. And, well, we managed to prove new things about this. For example, if such a space exists, then it has basis. In this paper, we prove that if such a space exists, then it has basis, and it has an unconditional basis, if and only if it is isomorphic to its square. But even on this question, we know very few things. I think that the most significant results in this direction that exist by now is a result by Wilson-Cuellar, who proved that a space which is not ergodic, so a space which does not satisfy that, should necessarily have all types P and all cotypes Q for P strictly less than 2 and Q strictly more than 2. But I think that's the best result we have.
Mm-hmm.
You mean that's for ergodic or for 2?
For both. So that's for ergodic, but in particular that's for 2, because a space which has 2 subspaces is not ergodic.
I see. Thank you.
All right. Okay, thank you so much. Any other questions or comments?
So I'd like to ask a question.
Yes.
Yeah. So your notion of largeness, D large, is a notion of largeness for a single space. I mean, they can be,
yes,
whether it comes from a local degree or non-local degree. It's a question of sort of a size of a single space.
Mm-hmm.
Now, if you look at the notion of tightness, this comes from sort of a large precision of subspaces inside of an ambient space. If you have a space with a basis, and then you look at and you pick a partition,
I see.
intervals, then you have sort of a relative precision. Is there a way of combining these two notions of degrees and sort of relative large precision inside? This looks like
that's a good question. That's a good question. I don't know. So in the paper, if you look at the paper, we have a more general notion than degree, which is called D families. So basically, D families, that's a notion for families of subspaces of a given space. So for example, you could, that does not need to be, that's something which is only defined relatively to the ambient space. So maybe we could build up something like that, but I don't know if there is really something like being D large and like being tight at the same time, but that's a very good question. Thank you. I will think about it.
Nice talk.
Right.
Thank you.
Thank you. Niels, you have a remark?
I do indeed. So it seems we got to the Danish section here. So first of all, thank you very much for such a nice talk, Noé. So if you go back to the slide with the operator ideals on it, you asked the question whether you could have one of these degrees coming from such a structure that wasn't actually an operator ideal.
Yes.
And the way you would normally generate such a class that has this absorbing property, but isn't closed under sums, is if you take a Banach space, say W, that doesn't contain a complemented copy of the direct sum of two copies of itself. So in particular, it's not Cartesian, right? Then you will generally need to take the span rather than, but you could still define your sort of norm by just taking factorization through a single.
Oh yes, nice. Thank you. Yes, I see. Yes, that's a very good answer. Thank you. Thank you very much for this answer.
Sure, no worries. Welcome.
All right, thank you, Neil.
Yeah, I have comments.
Go ahead, Valentin.
Noé, thank you for this very nice presentation. I just had a comment about Christian's comment. I mean, you have an equivalent characterization of tightness by myself and Gilles Godefroy, and which says that a space Y is tight into a basis on a FDG if it only embeds in a meager set of subspaces of subspaces of the space generated by subsequences of the natural basis or the natural FDD. So without entering into details, you have this characterization by Beck category, right? So every space can only embed into a meager subset. So I don't know if this can be related to Christian's question. I mean,
that's what I was thinking just before you talk about this, and that's a good thing. So the point is that our more general setting of D families, these families are defined as families that are G delta for a certain topology, which is very fine on the set of subspace, on the space of all subspaces, and that are closed under finite dimensional modification. So, well, on one side you want to be G delta, on the other side you want to be meager. So that's somewhat things that don't go well with each other. But the point is that the topology are different, and the topologies are very different. So I don't know. It's still a good question, but it will help. Yeah.
Yeah, the difficulty is that really to relate. I mean, this is very specific topology, right? The one related to subsequences of the basis. Yeah.
Yeah, that's it. Yeah.
Okay. Any others?
Well,
if not, yeah, go ahead.
I have a few
go
questions
ahead,
which are related to concrete spaces, but I have to think them through before I ask them. So that will be at a later stage. So.
Okay, so actually, yeah, we can talk on Discord later, maybe. Okay. All right, so if there are no other questions, I'd like to ask people maybe hang around a couple more minutes because we have some sort of a proposal that actually Noe came up with. So if you can actually listen to him for a couple of minutes, I'll appreciate that. Noe, again, thanks so much for the talk, and go ahead and
thank you.
And
thank you for the invitation.
Do the other presentation. So I'm just gonna stop recording.